Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to continue our lecture on bonding. In the previous video, we explored atomic orbitals and quantum numbers. Now we want to extend this concept to molecular orbitals, which form when atomic orbitals overlap as atoms come together to form bonds. Understanding molecular orbitals is important because they provide a quantum mechanical explanation for why chemical bonds form and why some are stronger or weaker than others. Every atom has its own set of atomic orbitals that define the electron density around the nucleus. However, when atoms approach one another, their atomic orbitals interact, leading to constructive or destructive interference of their wave functions. This interference determines whether a stable bond forms or whether the atoms repel each other. Constructive interference occurs when the wave functions of atomic orbitals have the same sign. So in other words, when they are in phase. This results in a bonding molecular orbital, which is lower in energy and more stable than the original atomic orbitals. Destructive interference occurs when the wave functions have opposite signs, leading to an anti-bonding molecular orbital. And this is going to be higher in energy and destabilizing. In other words, molecular orbitals are obtained mathematically by adding or subtracting the wave functions of atomic orbitals. Only electrons that fill bonding orbitals contribute to molecular stability, while those in the anti-bonding molecular orbitals, they can weaken or even prevent bond formation. This fundamental principle explains why some molecular structures are stable and others do not exist under normal conditions. From this principle, we can begin to construct molecular orbital diagrams between atoms to determine if they form bonds, what their bond order is, and even their magnetic properties. However, molecular orbital diagrams are most definitely not tested on in the MCAT. So instead, we want to take our understanding of molecular orbitals and move into a discussion on the patterns of orbital overlap. Chemical bonds are formed by the overlap of atomic orbitals, and the type of overlap determines the strength and properties of the bond. There are two primary types of covalent bonds, sigma bonds and pi bonds. Let's start with discussing sigma bonds. Sigma bonds are formed by the direct head-to-head or tail-to-tail overlap of atomic orbitals along the internuclear axis. The internuclear axis is just a straight line connecting the nuclei of two bonded atoms. And this overlap results in the highest electron density directly between the two nuclei, and that makes sigma bonds the strongest type of covalent bond. Now, sigma bonds can form in several ways. Sigma bonds can form through different types of orbital overlap. One common type is SS overlap, where two s orbitals form from different atoms overlapping directly, like you see here. Another type is the sp overlap, which occurs when an s orbital from one atom overlaps with the p orbital from another atom. Similarly, pp overlap takes place when two p orbitals interact. And finally, sigma bonds can also form through hybrid orbital overlap, where hybridized orbitals like sp3, sp2, or sp participate in bonding. We're going to explore hybridization in more detail shortly. But regardless of how they form, every single bond in a molecule consists of one sigma bond. Even double and triple bonds, one of those bonds will always be a sigma bond, while the remaining bonds will be pi bonds. And that helps us transition into our discussion on pi bonds. Pi bonds arise from the sideways overlap of two parallel p orbitals, resulting in electron density that's distributed right above and right below the bond axis, rather than directly between the nuclei, which is what we saw for sigma bonds. Because this type of overlap is less direct than sigma bonding, a pi bond is weaker than a sigma bond and more susceptible to breaking in chemical reactions. Now, a key principle to remember is that a pi bond cannot exist without a sigma bond. This is because pi bonding requires a stable internuclear framework, which is always provided by an initial sigma bond. So as a result, and this is what's really important to take away from this, is a single bond always contains just one sigma bond. A double bond always contains one sigma bond and one pi bond. And finally, a triple bond always contains one sigma bond and two pi bonds. Further, because of the different ways sigma and pi bonds form, bond strength and bond length follows a predictable trend. Sigma bonds, being the strongest, hold atoms together most effectively. But then the presence of additional pi bonds in double and triple bonds, that's going to lead to shorter bond lengths and stronger interactions. So in summary, a single bond is going to be the longest and the weakest, since there's only one sigma bond. Double bonds are going to be shorter and stronger than single bonds, and that's because they have one sigma bond and one pi bond. And then finally, triple bonds are the shortest and the strongest because they contain one sigma and two pi bonds. With that, we've completed objective 2, and we can now cover our last and final objective, hybridization. So far, we have established how atomic orbitals combine to form molecular orbitals and how sigma and pi bonds arise from different types of orbital overlap. However, if we just rely on atomic orbitals, only s, p, d, and f, we run into discrepancies when we're trying to explain the observed bonding geometries of many molecules. In some cases, the number and type of bonds an atom forms do not seem to align with its ground state electron configuration. This is where hybridization comes in. This is a model that allows us to reconcile atomic orbital theory with experimental molecular structures. Let's begin this discussion by analyzing what happens in methane, CH4, and why carbon forms 4 equivalent bonds despite carbon's electron configuration suggesting otherwise. If we look at carbon's ground state electron configuration, it is 1s2, 2s2, 2p2. This means that carbon has 2 electrons in the 2s orbital and 2 unpaired electrons in the 2p orbitals. Based on this configuration alone, you might expect that carbon would only form 2 bonds, one with each of these unpaired electrons. However, experimental evidence tells us something different. Carbon actually forms 4 identical bonds in methane, each with the same bond energy and bond length. More importantly, methane adopts a tetrahedral shape, meaning its 4 bonds are arranged symmetrically in 3-dimensional space with bond angles of approximately 109.5 degrees. So how can we explain this? The answer lies in hybridization, which is a theoretical model used to describe orbitals in a way that aligns with the observed bonding geometry. Now note, hybridization is not a physical process that atoms undergo, but rather a mathematical model that helps us understand bonding better. The mathematical background for hybridization, it comes from linear combination of atomic orbitals. This is a principle in quantum mechanics. In simple terms, hybrid orbitals are generated by taking weighted sums of atomic orbitals to produce new orbitals that better describe molecular bonding. Now, in the case of sp3 hybridization, carbon's s orbital, specifically this 2s orbital, its 2s orbital and these 3 2p orbitals are going to mathematically combine to form 4 identical sp3 hybrid orbitals. These new orbitals are degenerate, meaning they all have the same energy. They arrange themselves tetrahedrally to minimize electron repulsion, which aligns perfectly with the experimentally observed structure of methane. So this hybridization model explains why methane can form 4 bonds to hydrogens and why all 4 carbon-hydrogen bonds in methane are identical, even though carbon's ground state electron configuration initially suggests otherwise. Another key feature of sp3 hybridization is that these hybrid orbitals have 25% s character and 75% p character. This means they retain some of the properties of both s and p orbitals, but they're distinct from the original atomic orbitals. The increased p character also influences the bond angles, and it ensures that they match those experimentally observed 109.5 degree bond angles in methane. So in summary, the concept of hybridization allows us to explain why carbons form 4 equivalent bonds instead of just 2, and why methane adopts this tetrahedral shape. Without hybridization, we wouldn't be able to account for these observations. Now that we've introduced sp3 hybridization in methane, let's move on to another important type of hybridization, sp2 hybridization. To understand this, we're going to look at C2H4. This is a molecule where each carbon is bonded to 3 other atoms. It has 2 single bonds to hydrogens, and then it's double bonded to another carbon atom. Again, if we only consider carbon's ground state electron configuration, we might assume that each carbon can only form 2 bonds since there are only 2 unpaired electrons in the 2p orbitals. However, we know from experimental data of C2H4 that each carbon forms 3 equivalent bonds in a trigonal planar shape with bond angles of 120 degrees. This presents a discrepancy. Carbon appears to form more bonds than we would expect from its atomic orbitals alone. So to explain this, we again apply hybridization, which allows us to describe how carbon's atomic orbitals combine to create a new set of orbitals that much better match the molecule's observed bonding geometry. In sp2 hybridization, we take the 2s orbital and only two of the 2p orbitals. They mix together to form three sp2 hybrid orbitals, and these hybrid orbitals are equal in energy, so they're degenerate. In this way, we explain why each carbon forms three equivalent bonds in a flat trigonal planar structure. It also explains why we can have a double bond between the carbons. We leave a 2p orbital unhybridized, which is exactly what we need to form double bonds. So the three degenerate sp2 orbitals explain the three sigma bonds that each carbon can form, and then the unhybridized 2p orbital explains why we can then form a double bond between the two carbons. From here, another important characteristic of sp2 hybridization is its orbital composition. Since one s orbital and 2p orbitals are mixed, each sp2 hybrid orbital consists of 33% s character and 66% p character. Now let's move on to the last type we're going to cover, and that is sp hybridization. Here we're going to examine C2H2. What we notice is that the carbon atom forms a single sigma bond with hydrogen, and it forms a sigma bond with the other carbon and two pi bonds with the other carbon as well. And that's what helps form the triple bond between the two carbons. Once again, if we consider carbon's ground state electron configuration, we would think carbon can only form two single bonds. However, we know from experimental data for C2H2 that it forms a linear shape with a bond angle of 180 degrees, and that the carbon-carbon bond is much stronger than a typical single bond. So this suggests that there's some additional bonding interactions that are taking place. And so to explain this, we once again apply hybridization, which allows us to describe how carbon's atomic orbitals combine to match the observed molecular geometry. In sp hybridization, we take the 2s orbital and we take one of the 2p orbitals, we mix them together to form two new sp hybrid orbitals. These orbitals are degenerate, so they're equal in energy. Unlike sp2 hybridization, where one p orbital remains unhybridized, in sp hybridization, we actually leave two of the 2p orbitals unhybridized. And this is because we need to form that triple bond. These two remaining p orbitals are going to be oriented perpendicular to each other, and they are going to form the pi bonds that are necessary to form a triple bond. Because we know a triple bond is one sigma bond, we form that sigma bond with the sp hybrid orbitals, but then those two p orbitals that are overlapping with the other carbon's 2p orbitals allow us to form two pi bonds, which is necessary for a triple bond. So in other words, in sp hybridization, the two unhybridized p orbitals allow for a triple bond. And this explains why C2H2 has a linear shape and contains a strong carbon-carbon triple bond. Another defining characteristic of sp hybridization is its orbital composition. So here, each sp hybrid orbital consists of 50% s character and 50% p character. Now that we have discussed hybridization and how atomic orbitals mix to form new bonding arrangements, we can briefly touch on another key concept in bonding, and that is resonance. Hybridization helps explain molecular geometry and bonding behavior, but in some cases, a single Lewis structure is insufficient to fully describe how electrons are distributed within a molecule. And this is where resonance structures come into play. Resonance occurs when two or more valid Lewis structures can be drawn for the same molecule. And in this case, it's only differing in the placement of electrons while still maintaining the same arrangement of atoms. These structures are not separate entities that the molecule switches between. Rather, the actual electronic structure is a hybrid of all of the possible resonance forms. This delocalization of electrons, it helps increase molecular stability, and it also explains properties that a single Lewis structure couldn't fully capture. So for example, in the nitrate ion, NO3 minus, we can draw multiple Lewis structures where the double bond is placed between the nitrogen and a different oxygen each time. However, in reality, the electrons are delocalized across all three oxygens, making them chemically equivalent. Now, there are certain structural features that indicate the presence of resonance, and they include the following. Allelic lone pairs. These are lone pairs next to a pi bond that can be delocalized through resonance. Allelic carbocations. This is a positive charge next to a pi bond that can also be stabilized by resonance. Lone pairs adjacent to carbocations, so lone pairs on electronegative atoms can donate electron density to stabilize a nearby positive charge. There's pi bonds between atoms of differing electronegativity. So the more electronegative atom can then stabilize a negative charge through resonance. And finally, conjugated pi systems in rings. When you have alternating single and double bonds in a cyclic system that allows for continuous electron delocalization, like you would see in benzene. So these are 5 structural features that indicate the presence of resonance. From here, the follow-up question is, well, how do we determine the most stable resonance structure? And while multiple resonance structures may exist, sometimes they do not all contribute equally to the true electronic hybrid structure. The stability of a resonance form, it can be assessed using formal charge rules. Formal charge is equal to the number of valence electrons minus the number of non-bonding valence electrons minus the number of bonding electrons divided by 2. And again, you can use formal charge to assess the stability of resonance structures according to these rules. The first rule is satisfying the octet rule. So structures where all atoms have a complete octet, except for exceptions like hydrogen, are generally more stable. The second is minimizing formal charges. The best resonance structures distribute electrons in a way that results in the fewest overall formal charges. Then you want to place negative formal charges on more electronegative atoms. So if a negative charge is present, it is more stable when it's assigned to the most electronegative atom in the structure. On the other hand, positive charges should be placed on less electronegative atoms. And finally, if all of these rules are equal and followed for every resonance structure you have drawn, then all of the resonance structures contribute equally. So if multiple structures satisfy these rules equally, they contribute similarly to the resonance hybrid. And this is a topic we also covered in our MCAT general chemistry playlist if you want to revisit it. So in conclusion, resonance is an essential tool for understanding electron delocalization, which explains the stability of many molecules beyond what individual Lewis structures suggest. And by considering multiple resonance forms, we gain a more accurate picture of molecular structure and reactivity. And with that, we've covered everything we want in this chapter. I hope that this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.